In this video, we will talk about three kinds of thermal expansion in solids. That is our topic, which is like how the property of this thermal expansion is there in the solids. Since you're talking about solids in general, we what we use in our day-to-day life are the metals. Metals are generally the good conductors of heat and electricity. So the more you have the presence of the metals, generally in solids as well, the more you apply the heat, the more you ended up seeing the kinetic energy. And the more the kinetic energy is there, the more you will see the expansion. And the less the kinetic energy, the more you will see the contraction. Okay, that is the thermal expansion for us. Now in particularly solids, there are three ways through which you can actually see the expansion. We will be talking about one by one. So the first is linear expansion. Linear means a straight line expansion. So if the given solid is in the form of a rod or a wire, then on heating its length increases and the thermal expansion is called the linear expansion. Like let's say I have this wire here. Okay, after applying the heat it will become like this. So now its length supposed to be this, but now it reaches or it increased to this point as well. Okay, so this is my linear expansion. Now the amount of linear expansion depends on the original length, which you should know. Then the temperature that you are using, that is a rise in temperature. So the length can be used as capital L, the temperature can be used as delta T, because there has to be a change in temperature. Because whenever you see this delta sign, remember you're talking about change. Now it could be change for anything, here it is temperature. And lastly, the nature of the solid material, because that is also very important. If you are ended up using something which is like as I can say here, is taking so much of heat just to expand very small amount, so that is a nature. Okay, so in journal experiment we tend to not use such things as well. Okay, so that is why the nature of the material is also very important. So what you can do here is, if increase in length would be delta L, which is again because there is one length and now it has been increased, so you have to subtract both of them. So the change in length, so then delta is found to be proportional to the product of the original length and the increase in temperature, and that is the relation that you can see here. So with that you can see the relation here, which is delta L is directly proportional to the product of L times delta T, which is by nature itself you can see such a relation. So your formula could be something like this: delta L is equals to L, and then there is alpha, and then there is delta T, where alpha that you are looking here is a constant whose value depends on the material of the solid rod. I mean, again, that is why we use the nature of the solid material, because it is very important aspect here. And this constant is known as the coefficient of linear expansion of the given material. Means you should know what the value are supposed to keep it constant, because if you are using that material in a multiple places, so you need not to find the coefficient again and again. You ended up knowing one value and you can apply it everywhere. Okay, so this is the alpha. Other than that, the length and the temperature can be different, so that is why we keep it them in as a variable. So the formula that you ended up looking will be is coefficient of linear expansion is equals to increase in length divided by original length times rise in temperature. And you can also write it like this: delta L divided by L times delta T. That is for the linear expansion. Okay. Now, the coefficient of linear expansion of a solid in the form of a rod or wire is defined as the increase in length per unit original length per degree rise in temperature. Means again, what you are looking at here in the formula is same thing here as well. Whatever is your coefficient of thermal expansion, like what is the value that you ended up seeing in any material about when you see the thermal expansion, you can simply see here is that there is a increase in length, whatever the change in the length divided by or per se there is original length multiplied or the product of the change in temperature or rise in some temperature. Same thing is written here as well. Okay, its SI unit is k raised to the power minus 1, but commonly is expressed as per degree Celsius or degree Celsius minus 1, like that you can also write. Okay, the value of the coefficient of solid depends on its material. So here the values you can see now: lead is 5.1, aluminium is 2.4, brass is 1.8, iron is 1.2, platinum is 0.89. So these are fixed values. You need not to find every time when you are using this material, because again, you know the value of alpha, I can say here. Okay, so this is a linear coefficient or linear expansion, and the coefficient of linear expansion also you can say. Okay, now coming to the superficial expansion or the area expansion. In this case, what will happen if the solid is in the form of a thin sheet? Okay, what will happen is then on heating, its surface area increases and the thermal expansion is called the area expansion or superficial expansion. So let's say you have this block here. Okay, so you ended up having this big block. So you can see how the area has increased because of the expansion. So in such cases, you will about to use the this particular expansion, which is called area expansion. So the amount of area expansion, again, it will be the change in the area, so that is delta A, depends on the original area, rise in temperature, and again the nature of the solid material, it will be common. So your relation will be something like this: delta A directly proportional to the product of area, which is original area, times the change in the temperature. So with that, you can show the relation like this. That is delta A, which is change in area, is equals to A times beta, which is a coefficient of area expansion, times delta T, which is change in temperature. Okay, and what is the beta is, again, as I said, coefficient of superficial expansion or area expansion of the given solid material. Again, it will be also the same for a given material. So your formula will ended up being coefficient of superficial expansion is increase in surface area. There is increase in length. Now here is an increase in surface area divided by original area times rise in temperature. Few things are same, only few things are different. I mean, the arrangement of formula is always same. It's just the unit that you are taking. Okay, which is like here, this will be delta A divided by A times delta T. Now what you can say here is that the coefficient of superficial expansion of a solid is in the form of a thin sheet. How you can define it? That increase in its length per unit original area. Remember, increase in length or increase in its area per unit original area per degree rise in temperature. So you can denote it, or its SI unit will be K raised to the power minus 1 or per degree Celsius. Okay. The value of coefficient of superficial expansion of a solid depend on its material. It is found that for a given material, the value of coefficient of superficial expansion is twice the value of coefficient of linear expansion of that material, and you will get this relation. What they are trying to say here is simply, if you will see the change in the area like this, you might see that the length will also become twice of that. Okay, so if you see that there is a change in the coefficient of superficial expansion, you can simply have that in mind, that length is also the coefficient of linear expansion will become twice as well. That is how you can understand the relation. Now coming to the third relation, which is, or the third expansion, which is volume expansion. Now we are talking about volume, so we are including 3D shapes here as well. So when a bulk solid like a cube, cuboid, sphere, cylinder, all are 3D shapes, is heated, its volume increases. And so the thermal expansion is called volume expansion. Now in this case, since we are talking about volume, so everything depends on volume. So you have to look at the original volume, rise in temperature, and again the nature of the solid material. So your relation will be like, look like this. That is delta V directly proportional to the product of volume times change in temperature. Or you can also write it like this. Delta V is equals to V gamma delta V times gamma times delta T, which is gamma here is known as the coefficient of volume expansion of the given solid material. So alpha, beta, gamma, you can remember it like that, and the formula will be coefficient of volume expansion is equals to increase in volume divided by original volume times rise in temperature, and you can also write it like this: delta V divided by V times delta D. And how you can define the same? That coefficient of volume expansion of a bulk solid is defined as increase in its volume, okay, per original volume per degree rise in temperature, and its SI unit is also the same, which is K raised to the power minus 1 or per degree Celsius. And the relation between the linear expansion, the coefficient of linear expansion, and the coefficient of volume expansion will be this. You will see that there will be 3 times the coefficient of linear expansion can be increased if there is an increase in the volume expansion. So that's how you can actually relate the linear coefficient of linear expansion, coefficient of area expansion or a superficial expansion, and a coefficient of volume expansion. I hope it is clear to you. Thank you.